we're going to start today with the blackboard. So last class, we were talking about this shrinkage method. And let me summarize the main lessons we should have taken away from the shrinkage. The main lessons. And I think the main thing was the thing we said right at the beginning. That is, sometimes you want to seemingly make your model worse, make it biased, and that will actually improve the error. So let's say be adding some bias in, adding some bias can actually improve the error. Let's say overall error. And I think this is extremely counterintuitive, and that the kind of thing that you would not think of sort of on the face of it. Adding some bias can actually improve the overall error. And specifically, how does it do this? It does this by reducing the variance. Okay, and remember the bias is how far away our procedure is from the true average. That's the bias. The bias equals the average of our procedure, the expected value of whatever we're estimating. Last class, it was this mu. So mu hat minus the true mu. So we have some procedure. Our procedure depends on the data that we collect, but on average, is it giving the right answer? If it's giving the right answer on average, then we say it's unbiased, and we might want to give that up. And the reason we can reduce that is it reduces the variance. The variance is how much our procedure is changing from time to time. So if we look at mu hat minus its mean, so sometimes mu hat is a little bit above its mean, sometimes mu hat is a little bit below its mean. If the variance of that random variable, the variance of this stuff, is small, then if we can trade a little bit of bias for improving the variance, and that trade can be beneficial. Overall, it can improve the error. That's the main lesson from last class. And we had an example of this. The example was just shrink all the parameters. Shrink everything. So shrink everything. Shrink everything. So whatever you were going to output before, multiply it by some lambda. So mu hat, we called it lambda, is lambda times the honest mean. Let's say that times the mean. This was the kind of thing we did last class. Just shrink when you're trying to estimate something. Just instead of estimating the full thing, just multiply it by some lambda value. And as that lambda value is a little tiny bit less than 1, then this will reduce the variance by a lambda squared, and so you can get a favorable trade-off. This in particular, the James Stein estimator is a way to automatically calculate this. So lambda JS is some automatic way to calculate lambda. That works. But in general, if we don't have some automatic way to do it, we're going to do it the way we do all the data things in this course. So thinking like a data scientist rather than a statistician, instead of coming up with some exact formula, we're just going to check, try different lambdas using validation. So just make a validation set, try it out, and make sure that it works. And we saw last class that if you go too far, if you make lambda really, really small, like lambda equals 0, then you're adding too much bias. So we want to make a trade. We want to trade a little bit of bias for a little bit of reduction in variance. If you trade too much, then it will go awry and actually be much worse than the other way. So that is the main lesson from last class. Let me see. Was there anything else? I want to have some notes here. Let me see if I'm forgetting anything else. Okay. Okay. Yeah. The amount is important. Okay. That is all recap sort of from last class. Any questions or comments about any of this stuff? Okay, so now we're going to keep this idea of trying to trade. We're going to trade a little bit of bias for reducing the variance. But we're going to see if there's better ways to do it. So instead of shrinking everything, the question we're going to ask is, can we shrink different factors individually? And we're specifically going to look in the context of linear regression. So different example. In linear regression, we have our estimator is y hat. That is a linear combination of the x's. So it's beta hat 1 times x1 plus beta hat 2 times x2 plus dot 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 plus beta hat n times xn. If we were going to shrink everything, we were saying, oh, let's just shrink everything. Then we multiply this by some lambda, and that would multiply every single thing by lambda. And so you can think of the shrinkage thing is multiplying every individual. All parameters are all shrunk by the same lambda. Params beta hat shrunk by the same lambda. So if we were doing what we did on Monday's class, we would shrink everything by the same factor lambda, and we go, oh, okay, that's great. Like it improves a little bit, the error, and so on. But now we're going to ask, can we do better by shrinking unequally? By shrinking some more than others? That is the question we're going to try to answer today. Can we do better by shrinking some more than others? And here is one way you could do it. Option one, you could just literally have a whole bunch more parameters. You say, take the beta hats you get from linear regression, then let's make a bunch of different factors, lambda 1, lambda 2, dot, 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 lambda n, and shrink all of them individually and try them all individually. Okay. Unfortunately, this is a bad idea. Trying to just go from one parameter to many, many parameters is a bad idea. And the reason is there's just too many parameters. Too many parameters to mess with. I guess these are hyperparameters, right? To mess with. And so once again, when you're estimating things, if you have too many parameters, you get into this overfitting thing, right? If you have a lot of parameters that are as many as data points that you have, then there are many different ways you could set them to fit the data that you have that does not match what you want. So adding in lots of parameters like this is not a great idea. Another way to say it is that it is hard to find the right parameters, hard to find good parameters. So last class, when there was only one parameter, we could just try it, and we had this like spectrum, and we thought, oh, 92% is pretty good. If you have hundreds and hundreds of parameters, then that will not work, and that will not be good. So that was option one. But option two is what we're actually going to do, which is the so-called ridge regression. Ridge regression. I have absolutely no idea who named this thing, because as far as I can tell, it's got nothing to do with ridges at all. So who named this thing ridge regression? I don't know. Another name for it is called L2 regularization, and that one actually does make sense to me. I will explain what this means momentarily. Regularization. And the idea in L2 regularization or ridge regression is that we are going to simultaneously shrink all the parameters. We're going to have one knob, I'm going to call it alpha, that is going to shrink all the parameters, beta hat 1, beta hat 2, all the way to beta hat n. It's going to shrink all of them. It's not going to shrink them an equal amount, so not like we did over here, not an equal amount, but there's one knob that tells you the strength of the regularization, and then the model will decide automatically, based on the strength, how much to shrink. So that's the idea. The idea, we have one hyperparameter, and typically it's called alpha. Some people call it lambda, like we did before, but let me call it alpha so we don't get it mixed up. And this hyperparameter will tell you the strength for the strength of the regularization, the strength of shrinking. So before we had these lambdas, and lambda equals 1 was no shrinking, lambda equals 0.5 was a lot of shrinking, and we have this one hyperparameter alpha that is sort of going to tell you what it is doing. So alpha large, that will go to lots of shrinking. So the lambda is small. And alpha small is very little shrinking. Minimal shrinking, minimal. But we are going to shrink all the parameters. So it is fundamentally the same kind of idea as before. It's just we're doing it in a different way. And this one parameter, once we set it, then the model will automatically decide how much to shrink each thing. So this is the big advantage, is the model, or the model uses data and the strength alpha, to automatically decide how much to shrink things. To shrink each beta hat I. So in other words, instead of shrinking them all an equal amount, there's some method by which we actually go to the data and we let the data set decide how much each beta hat I should be shrunk depending on the alpha. And this is a great system. I think if you can conceptually think of it like this, this is what we want to do. This all sounds very nice. We have one parameter, so not like lots of parameters. The model is going to automatically shrink things depending on the strength. We have like one knob we can turn. This is a great setup. You might ask, how on earth are we going to achieve this? This seems very, very complicated and fancy. And the thing that we do is we just slightly modify the mean squared error. So the mean squared error before, the mean squared error of some beta hats. So I'll write beta hat like this. It was the sum of the squares of the difference. The sum of the true yi minus, let me write, what should I write here? Let me write it out. Beta hat 1 x1 plus dot 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 plus beta hat n xn. Okay, and let me write out as superscripts the thing over here. So going from 1 to the number of data points. That's the mean squared error. Okay, I have to divide by the number of data points. Let's do that. 1 over n data. Okay, that's the mean squared error. So you tell me what beta hats you want. I calculate for every single data point in the data set what your estimate is. I compare the estimate to the real answer in the data set. I take the difference, I square it. I average over all the data points. That's the mean squared error for some parameter. And the ordinary linear regression, we said, is minimizing just the mean squared error. How are we going to achieve this thing that we want for ridge regression? We are going to add on a penalty term. So the mean squared error plus what I call alpha times a penalty. Alpha. Let's do alpha in red. That's a cool color. And I'm going to call this thing the regularization penalty. Regularization penalty. And it's a function of beta hat. So just like the mean squared error is a function of beta hat, the regularization penalty is also a function of beta hat. And what is it? It's a very simple formula. For ridge regression, you use the sum of the squares. The sum from I equals, let's use a different letter. It's not I. Actually, let's write it out. Let's write it out as a big sum. It's beta hat 1 squared plus beta hat 2 squared plus dot 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 plus beta hat n squared. And this thing is sometimes called the L2 norm, the L2 norm of the vector beta hat. And this is why it's called L2 regularization. We're using the L2 norm to construct this regularization penalty, and we add on this penalty onto the mean squared error. And what is ridge regression? Ridge regression says the new values of beta we should choose minimize this thing. So ridge regression, one formula, ridge regression. Find the minimum, find the beta hat that minimizes this sum, the mean squared error, beta hat plus alpha times the regularization penalty. Regularization penalty. So in other words, ordinary linear regression just minimizes the mean squared error. Ridge regression minimizes the sum of the mean squared error plus the regularization penalty. And what effect does this do? Okay, what effect does this do? Net effects. Net effects. The main one is exactly what I said, is all the beta hats will be a little bit smaller. Will be a bit smaller than they were before. And I'll say in ordinary regression. Okay. So it is doing this thing of automatically shrinking everything. Why is it true that all the beta hats will shrink? Well, the regularization penalty says you are paying a price for having large beta hat values. If your beta hat values are very large, then you will have a lot of penalty term added on to your score. You can think of this as a score, right? This is the score, the ridge score, the score. And if you are estimating things and you have found the absolute minimum of the mean squared error, but the beta hats are very large, then you are paying a big price over here. And the alpha value controls how big of a price you pay. If alpha is extremely large, then this term is very, very big. If alpha is really small and close to 0, then this will be some positive number, but not a big number. But in any case, you are paying some amount of penalty for this extra term. And therefore, you can optimize it. You can always, when you're minimizing in the ridge regression, you can always improve things a little bit by shrinking the betas. When you shrink the betas, this term will get worse, the mean squared error will get worse, but this term will get better, and you can shrink just a tiny, tiny bit to improve the overall situation and shrink the betas a little bit. So this is due to shrinking that error term, that penalty term. Okay. So if you think about the optimization, that is what's going on. This is the main idea for bridge regression. Are there any questions or comments about this main idea? So we're shrinking all the parameters. You might say, hey, this is so silly. But we had the best answer before. We were minimizing the mean squared error before. Why on earth would you do this thing and give me an answer other than the one that minimizes the mean squared error? You have this artificial thing added on that you just threw on there for no reason. Why would you do that? And again, the reason is what we discussed on Monday's class. The reason is to do this. We are going, by shrinking everything a little bit, we are adding in some bias so that the beta hats we get will no longer be like the best possible beta hats. But by shrinking it, we are reducing the variance. So that is the hope, is that even though the ridge regression compared to the ordinary regression, the ordinary least squares as some people call it, even though it's kind of silly and you're saying, I don't want the best answer, I want the best answer to some other question than we care about, we are adding in some bias, we are not getting the best possible beta hats in some sense. Overall, we're going to improve the error because we're reducing the variance by shrinking everything just a little bit. And we've done it in such a way, we have gotten these nice features, which is we have avoided using a lot of hyperparameters. There's only one hyperparameter alpha that tells you the strength of the how much you want to do this, right? So the alpha is the only thing you have to specify over here. Once you've specified alpha, then you can minimize this whole thing. And the model uses the data and the strength alpha to figure out how to shrink each beta hat. And the reason we're doing that is because it's the same kind of minimization problem as before. The thing that minimizes this depends on the data. Depends on the data. So in other words, because the data is appearing here, let me highlight where it appears. Right, the data still appears here just like it did in the ordinary least squares, the ordinary regression. And so now we're trying to find a trade-off. We're trying to trade off shrinking the beta hat values. If we can shrink the beta hat value a lot, that will improve this a lot. If shrinking the beta hat value a lot would hurt the mean squared error, then we won't do it as much. On the other hand, if there's a beta hat that you can shrink down to 0 to kind of remove it from here, and it has no effect on the actual difference between the y's and the x's, then it'll get shrunk down to 0. So you see, it can automatically detect which ones can be shrunk a lot and which ones can be shrunk just a little bit. Let me write this down. Let me say if beta hat, let's say I, can be shrunk to 0, can be shrunk to 0 or near 0, let's say near 0, without hurting the mean squared error term much, then I'll call it the ridge minimization. The minimization will do it. We'll do that. So in other words, if it's possible to shrink down a beta hat value a lot without affecting the mean squared error much, then this penalty term will say, hey, we should shrink that really small to make that penalty term as small as we can. And we will only stop shrinking when it starts to affect our error. And therefore, parameters that don't matter much should get shrunk to 0. So that's the idea. So the idea of this is if it doesn't matter much, it should be shrunk to 0. Shrunk down to 0 if it doesn't matter much. Doesn't matter much. Okay. On the other hand, the reverse is also true. Let me not write the reverse down. I will just say the reverse out loud. In contrast to this, suppose there's some beta hat that matters a lot. The beta hat is really, really important for predicting the y's. The beta hat times the beta hat 1 times x1 is the most important term out of all these terms for predicting the y hats. If you change the beta hat 1 even a small amount, then you will get really bad predictions. Well, in that situation, the ridge regression minimization will say, hey, even though we could shrink it and sort of like improve on this penalty term, let's not do that because it would make this term much worse. So things that are really important will get shrunk only a tiny, tiny bit. Things that are sort of not important, they should get shrunk a lot. That's the idea behind the ridge regression. Okay, so we're going to move to showing you some examples in Python. But this is a good time if there's questions about the theory or what's going on or why we're doing any of this stuff. It is a very weird idea. Like if someone just told you, hey, this is what it is, you'd be like, what are you talking about? Why would you add on this weird term? What's the point? Hopefully at this point, it kind of makes sense why we're doing this and where it comes from. Questions?
How do you know which variables are less important?
That's what I'm saying is the model will do it automatically. So the model will say, look, beta hat 1, if I change beta hat 1, that would really make our mean squared error bad. So don't touch beta hat 1, right? Because I want to minimize the mean squared error plus something. And so the model is thinking, it's like, when I'm minimizing this, let's try changing beta hat 1 and see what happens. Oh, don't do that. That's a bad idea. It makes the mean squared error really bad. All right, what about beta hat 2? Let's try shrinking beta hat 2. Oh, that doesn't affect the mean squared error. We can shrink that all the way down to 0. Look at all this like improvement we've picked up by shrinking the error over here. And we have not much loss in the mean squared error. Therefore, I can shrink beta hat down to 0. So it's sort of automatically doing it. So that this minimizes. When you minimize things, that's a kind of thinking, right? And in this step of saying minimize the thing, that is where it will, quote, automatically do the thinking of what matters a lot and what matters not much. This is a bit like in your project 1, if you used subset selection, you were minimizing, right? You're saying how many features can I add on to minimize the error, and that is automatically finding the ones that matter, right? Because it's doing this minimizing procedure. That's where all the thinking happens. Yeah, great question. Anyone else? Okay, let's go to an example. So the first example I have is a very dopey synthetic example, and I'll show you that one. And then I will show you a real example with a real data set from the textbook. Let's see if I can find the one that I'm talking about here. And this is an example we've seen before. We've seen it one way already. And so now we're going to do the same kind of thing that we did before, but do it with ridge regression instead. Okay, and here's the code. Let me see if I run. Can I run all? Will it complain? Okay, maybe I didn't want to run all because it's taking a long time. Okay, wait, it finished. Okay, so this is the data set that I showed you before. There are 5 x values. There's x1, x2, x3, x4, x5, and they're very highly correlated, right? So the correlation between x1 and x2 is 0.95. The correlation between x1 and x3 is 0.87. These are all very highly correlated x values. And I have basically two problems, two completely separate problems. I have a y1 and a y2, okay? So if you look at my table, I have x1 and x5, that's my data, and then I have 2 different things I'm trying to predict. Think of them as 2 completely separate problems, predicting y1 and predicting y2. Okay, and we used this example a while ago to argue that you should not just look at the x values to decide which to keep. You cannot look at the x values and say, let's just keep x1. You cannot decide that just based on the x's, and the reason is for one y value, you should do one thing, and for the other y value, you should do another thing, and therefore there's not enough information in the x's alone. You want to combine the x's with the y's to make decisions. So let's see. And I think ultimately the way we showed this is we did forward selection. This is the forward selection for y1, and in forward selection for y1, only one variable is the best. If you add on more variables, it's getting worse. So with one variable, it's the best. And in fact, the best feature to add, what was the best feature to add? That'll be good to know. So we tried all the features, and the best one to add was x5. So So the best model is only using x5. So when you're predicting y1, you should only use x5. You should ignore x1, 2, 3, 4. x1, 2, 3, 4 are not helpful for predicting y1. Only x5 is needed. And this is kind of tricky because they're all highly correlated, right? So if you weren't being careful about this stuff, x1 kind of is predictive of x5, and therefore, like x1 is a good estimator. It's just that x5 on its own is better than x1. Okay. On the other hand, here's y2. y2, same exact thing, but for y2, you should use 4 variables. Why should you use 4 variables? In this case, we found x4, x3, x1, and x4. Did I say 4 already? 5, 3, 1, and 4 was the best thing we found. You should only use 4 variables. And actually, secretly, if you look at how I created these things, under the hood, this is all a synthetic example, then y1 actually only depends on 1 variable, but y2 depends on 4 variables. So it is kind of doing the right kind of thing. There's some noise that's built in, and they're the same, very similar formulas, but y1 depends only on one thing, and y2 depends on another thing. Whoa, this is new. You can mouse over a variable, and it will show you the distribution. That's cool. That was not a thing last year. Can I do it for x1 as well? Let me, x1. No, x1 is an array, but y1 is a series. So there you go. That's a nice feature. Okay. So that's what we've done with this thing so far. We're about to do the same kind of thing and see what happens when we do ridge regression on it. But are there any questions about the setup? All right. So here is the ridge regression, and it's the same kind of thing. What you have to remember is for ridge regression, you have to pick an alpha value. This is one thing that you cannot ever forget, is that it is all highly, highly dependent on the value of alpha. So let me write that in so we don't forget. Choose alpha, and then, and so I wrote a little code here that is trying it for some alpha. And so this will try a whole bunch of them. It will do a train test split to try it out. Okay. So what do I get at the end of the day? It's a graph like this. What is going on in this graph? Well, the bottom axis here, the x-axis, let me make this a little bit bigger if I can, is the ridge regularization parameter. That is what I called alpha. And we're going on a scale here from really small values of alpha to really big values of alpha. Here, alpha is 0.01. Here, alpha is 1,000. And it's on a log scale because sometimes you need to try many different sizes of alpha. And this lets us try many sizes of alpha. On the y-axis, I have what are called the weights, and they are labeled with the weight for x1, the weight for x2, the weight for x3, the weight for x4, and the weight for x5. These are the coefficients. These are the beta hat 1, beta hat 2, beta hat 3, beta hat 4, and beta hat 5 for the model. And let me just check. So this is for y1. Yeah, okay, this is for y1. And what this is saying is when you have almost no regularization, when the strength is very little, then we're saying x2 should be -3, x4 should be close to 0, x3 should be like 0.5, x5 should be like 1.5, the coefficient for x5, I mean, and the coefficient for x1 should be like really high, up to 3. You remember y1 actually only depends on x1. y1 is actually a function only of x1. The other ones, the purple, the green, the red, and the orange, are all noise. These are all noise, right? The true truth of the situation, I constructed it, and I know, is that the y1 equals x1 plus some noise. Actually, what is the true coefficient? Let's go up to where I made the model and peek at the answer. B equals 2. So the true thing that we actually want in this example, let me write this down. In this example, the truth is y equals 2x1 plus noise. And the problem is the noise, all these x's, x2, x3, x4, x5 are highly correlated with x1. And that is like screwing us up, right? We have all these, we don't know what is noise and what doesn't depend on these things, and we have this like finite data set. And so x2, x3, x4, x5 are screwing us up. That's what's going on. This is the truth for y1. Okay, and if you look at what we have with no regularization, with no strength on the regularization, when the alpha value is very small, that's almost like ordinary linear regression, is you see, for example, the coefficient on x2, we think x2 matters a lot. We think x2 matters as much almost as x1, right? And that is just pure noise. Like we've been bamboozled by the randomness. This is very, very wrong. Okay. We can now improve the model by boosting up the regularization. So we can say, please, 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 we're going to boost up the strength of this regularization and shrink the parameters so that we improve our error. And you can see that this thing that is pure noise, the x2 that is pure noise, is shrinking very rapidly. So by the time we get to an alpha value of like 5 or like 3, an alpha value maybe 2, an alpha value of 2, then x2 has shrunk a lot. And this is sort of it recognizing that the x2 does not really affect things very much. x2 is probably mostly noise, so we should shrink it as much as we can to improve the model. On the other hand, x1 also shrunk. The true value of x1 was actually 2, right? So this being at this point right here is where we would like to be. The coefficient for x1 should be 2, because that was what the model was doing. So actually, we've shrunk it from 3, which was kind of too high, down to a little bit less than 2. So we've shrunk it a little bit past where we need to go, but it is an improvement in the model. So this is the idea of ridge. You can see in these kinds of plots with the strength on the x-axis that as you increase the strength, all the coefficients shrink, and they shrink towards 0. Eventually, if you go too strong, then your model is just outputting 0, just like the very dumb model we had, fully shrinking by 0. That's not great. And so you want to balance how much you shrink. And we did a lot of test sets to figure validation sets to figure out that this dotted line is the optimal answer. And the optimal answer is quite nice because the x1 value is pretty close to what it should be at 2. Of course, it's not perfect because it's a finite data set, and that's what we got. So that's my little story for this y1 and the ridge regression, which is your first example of seeing it in action. Are there any questions or comments about this picture or what it represents or what's going on? I am curious, you know what we should do? Let's run it again. This is maybe a dangerous thing to do in a live lecture, but let's change the seed. So if I change the seed, we'll get a new data set, and it'll look different, and we'll see what happens. Let's change that from 1 to 2. Let's change it to this number. That way you know I'm not cheating. Oh no, has to be a little bit less. Okay, let's delete some of these characters. All right, is that a good number, Mr. Computer? Run. Generate the data. How did the picture change? Variables. Okay, here we ran it again. We got a new picture. And this time, x2 was like, just by chance, it thought x2 should be very positive this time. Remember, y does not actually depend on x2. It depends on x1, and x2 and x1 are very highly correlated. And again, it recognizes sort of if you do ordinary least squares with no regularization, you get a very high x2 value, and then you shrink it, at least it's gone down from 6 to 2. So it still thinks it depends on x2, but at least the dependence is smaller. Yeah, this is not going great for us, right? The thing that actually depends on x1, that should be 2 times x1, and it thinks it's negative. So we got kind of unlucky with the data set. Let's try one more. This is fun. I will delete this, and I will add in some more random digits. There we go. Maybe that's too many. Let's do that. Okay. Let's see what happens. Okay, run. And we see, okay, this is a nice one. Okay, so once again, shrinking. This time the parameter was a little bit higher. And of course, it'll never be perfect because I think we only have like 10 things in our data set. But it is shrinking, whatever it is. Actually, that's another thing we can play with. What about the number of data points we have? How many data points do I have? df, x1, n equals 100. Secret data of n. Let's instead of having 100 points, let's have 500 points. Let's have 1,000 points. That's exciting. And let's run it again and see how does that change it. So if I make the number of points a lot bigger, is it getting better? That's a fun thing we can try. Okay, look at this one. That's a beautiful one. So in this one, x3 started out at negative 1.5 without any regularization, and we've shrunk it quite a lot to shrink the x3 down very close to 0. And the x1 shrunk from 1.5, which is pretty close to where it should have been. It has shrunk all the way to a very small positive number. So we were sort of, at least we got rid of the dependence on x3. Okay, that was the example with y1. Now I'm going to move on to the example with y2. Very similar story, but I want to show you what's going on with the y2, because the y2 depends on all the other ones. I think so y2 depends on x2 plus x3 plus x4 plus x5. So it depends on all of them. And to make it sort of the same size, I also divided by 2 plus noise. I think that was the formula for y2. Let's double check. Let us double check. The formula for y2. Okay, there you go. Depends on 2, 3, 4, and 5. Okay. And what does that look like? Let's see. So does it look any different? Look at that. This looks very different. Oh, this is the different plot. That's why it looks different. Okay, here we go. This one, oh, it's saying, actually, you were doing better with almost no regularization. That's very interesting. Okay. Let's run it one more time. Let's put in and see if we can see something more interesting than do nothing, which is, I guess, sometimes the answer, but not very exciting. Okay. This time for y2, we're in the y2. It's saying, again, how to shrink things. Well, right, you want to shrink as much as you can, but not too much. This time, everything is positive. You'll notice this starts at 0.4. The actual value of 0 is all the way down there, so somewhere below. And it's kind of going up for a bit, and then it starts to shrink. So eventually, they will shrink down to 0, but they might increase along the way. An individual thing might increase, even though on average, they sort of all go down. And in this case, what are we finding? X1 is the bad one. Oh, X1 went up? Oh, no. So things don't always work. Okay, I think we've had enough of this silly example. Let's go to a real example with a real data set. And again, it is a data set we've seen before. And that data set is the hitters data set. Let's see, where did my hitters go? Here it is. Yes, okay, lovely. Okay. Hitters. So you remember hitters. You might be more excited about hitters now after baseball season. We're trying to take these individual people who play baseball. We're taking their stats, like how good they are at baseball, how many bases did they run in, and how many home runs did they hit, and we're trying to predict their salary. So presumably better baseball players get paid more, which is the kind of thing we're getting at. And we did this with ordinary least squares, but now we're going to do it with ridge regression. So here are the coefficients we got for the ordinary least squares. And if we do it with ridge regression, we use this ridge function from scikit-learn, and we try a whole bunch of alpha values on some grid, and we plot it. And it looks like this. Same kind of thing as before, right? Very small ridge values over here, very large ridge values over here. Now there are many, many coefficients that correspond to the various factors of the players. The league, the number of hits, the home runs, this kind of stuff. And you can see they shrink towards 0. The other thing you can do is you can plot the error. So using validation to find the best error, this is as a function of the strength of the regularization, the alpha parameter, what is the test set RMSE, or the validation set RMSE. And you can see it starts out here, and then it goes down, and then it goes up. We want to find the minimum. There is one thing that should bother you, though, which is, yes, it is an improvement. But if you look at the scale of this y-axis, it's a very, very, very small improvement. We started out at 341.5, and we got down to just under 340. So out of 340, we've improved by 1. So this is like a 0.1%, a 0.2% improvement in our error. This is not great. We're doing all this work. We should get at least a better improvement. So what's going on with this? And that is the subject of the first mathematized question. Let me open this one back up. Maybe you can see a hint in this situation on what's going on, or if you want me to scroll around somewhere else, I'm happy to do so. But the first mathematized question asks, why did it not improve more? Let's see, mathematize. This is the wrong one, okay. We want maybe this one. Mathematize. Yeah, hitters dataset improvement. Here we go. The improvement by using regularization seems extremely tiny on the hitters dataset. Are we doing anything wrong? Is there anything that looks suspicious to you? The access code might have changed from what it was before. So apologies if you entered the wrong room. I'll give you time to find your way to the room that is being recommended over here. But yeah, what's suspicious about what I did? And indeed, there is some kind of error lurking. All right, there's like 30 seconds left. Put in your guesses. Maybe we'll do a revote if there's not a consensus. Maybe you have no idea what's wrong with it. Maybe I should bring the graph back up to help you out, actually. The lab. Okay. This lab is from the textbook. They talk about it in the videos as well, so it's a good one for the lab. Yeah, I think you can see something suspicious in this plot. Okay. Okay, and let's take a look at what people said. Maybe I can glue this one to here. This is the wrong class. Okay, great. Wait, maybe not. Yeah, hitters, zetas. Okay, this one we close. Okay. All right. What did people say? What is wrong with this? Okay. I don't know. Lots of people saying I don't know. Tuning, values, range, predictor. Standardization improves. This one, standardization with a lowercase s. All right. Let's see if anyone said anything interesting in these submissions. I don't know. We are doing okay. I like this one. We do not pay attention to the scale of the predictor's values. And so this is really the first hint that something is wrong, is when you look at this graph, almost everything is near 0 except for a couple of these guys that are really not 0, right? This one is like in the hundreds, and these ones are close to 0. So that is something kind of fishy. On the face of it, you might think that this means that this one is really, 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 really important, and the other ones are less important. This one, by the way, this purple one is division. Division. Which division are you in? Are you in the North Division or the South Division? This is one of these dummy variables. Same thing. What is this red one? Red one. Red one is league. What league are you in? There's a North and a South and an East and a West or something. So that's kind of funny. Let's see if anyone else noticed. Someone said we didn't do anything wrong. We did in fact do something wrong. Okay, great. Let's let's figure it out. The model only seems to be tuning 3 parameters. This is a great astute observation. It seems like most of them are being left completely alone, and the model is only messing with these 3 ones. The league and the division and this yellow one, I think, is the new league. The new league. So the model seems to, for some reason, be ignoring all of these things and only dealing with these 3. And that is absolutely true, and that is a problem. Okay, let's see. Some people are saying must standardize. Lack of standardization. I think we need regularization. We are using regularization, so that's not the thing. So some people are saying standardization. So some people have put in standardization, and standardization is in some sense the right answer. But why is it the right answer? What is it? Standardization. And so standardization is the idea of like rescale things to make all the values about the same size. Rescale things to all be the same, let's say the same-ish, that's a good word, the same-ish size. So we're gonna change the size of all the predictors x and rescale them to make them all the same-ish size. And you might remember several classes ago, I told you standardization does not matter in linear regression. And that's because if you do beta hat 1 times x1, that is the same thing as beta hat 1 times 7 times x1 divided by 7. So in other words, whatever you do to the x's will just get undone in the beta hats. So for linear models like this, beta hat 1 times x1, if you rescale your x's by 7, you'll just rescale the beta hats by 7. So these will cancel out and it won't do anything. So it does nothing for ordinary least squares. Does nothing for ordinary least squares or ordinary regression. Let's say ordinary least squares regression. This will have no effect. But we're not doing ordinary least squares regression. We're doing the ridge regression. Let's scroll back to the formula for the ridge regression. It was this. So the ordinary least squares, if you change the x's, it will do nothing over here on its own, because whatever you do to the x's will get undone in the beta hats. But now all of a sudden it matters. Does anyone want to say why does it matter in ridge regression? Why does it matter all of a sudden? Yeah.
Because they want to analyze the large vectors because, and when the scale of predictors is small, they have usually larger beta, and That's why it's scale.
Yes, exactly right. So even though the x's and the betas, you can undo any change you do to the x's get undone by the betas, the way we wrote the model down, we're looking at the honest to God size of the beta, take the value and square it. And so if the value is very large, when you square it, it's going to be some huge number. And so the relative sizes of the betas, it really does matter here, right? And so if you make one of them 10 times bigger, then the thing that I said earlier, right? I said the model can figure out which ones to care about. Well, the model will care about the biggest ones because the model is trying to minimize this square thing. So if the values here are really, really big, then it will care a lot about those individual values. So sort of as an emergent net effect of what we have done is the model cares about large betas. Model cares more about large betas. Model cares most about large betas. This is a property of what we've done, and you can see it right there in the formula, in the sum of the squares. All of them are getting squared and added together. It cares about the size. The real, you square the number and care about the size, and that cannot get canceled out. So if you multiply beta hat 1 by 7 over here to cancel out something in the x1, then you're going to multiply by 49 over here, and that really will stick around. So the thing that I said standardization does not matter for a linear squares regression, it does matter. It does matter. It does matter for ridge because 7 times beta hat 1 squared is not the same as beta hat 1 squared. So in other words, when you square it, if you multiply it by 7, then that will make a difference, and you'll get a different answer. And that is exactly what's going on here, is if you look at what we've done, is for whatever reason, the division and the new league and the league, these are huge beta hats. They're really large beta hats. So basically what the model is doing is it's doing ridge regression on these 3 features, and it's doing nothing to all those features. And the reason is the model knows I should only care about the biggest ones, and these 3 are the biggest ones. Everything else is so small in comparison, it is not worth my time to mess around with. I'm doing 100 squared plus like 0.01 squared. Okay, we'll just ignore the 0.01 and play with the 100 squared. And so if you look at the coefficients that we got, it is indeed like that. All of the coefficients are small numbers. The at-bat coefficient, the number of times you tried, is negative 1.87. The hits, how many times you hit the ball and got on base, 6.5. So relatively, 6.5 is a lot bigger than negative 1.8, but it's a lot smaller than the division, which is negative 116. And when you square them, it gets even more extreme. So the model is basically ignoring all the numbers except for division, league, and I think there was one more. Maybe that one got smooshed up somewhere. Does anyone see the next big value? What am I looking for? New league, negative 3. Maybe it wasn't negative 3. Was it negative 3? Let's go to the picture. There's something that was at negative 25. Negative 25, positive. So 51, negative 116. I don't know. Maybe it got changed. Maybe this is already done. This is 0.01. Maybe it's already done some regularization. Okay, let's not worry about that for now. So that's the problem. These numbers are all too different, and so the ridge regression really cares about these actual numbers squared, and we want to make them all approximately the same size so that it can normalize things. So that the solution to this problem is standardization, which is solution. Make sure the betas are all on the same scale. Make sure betas are all approximately same size or same units or something like that, same size. And one method to do that is very simple, is called normalization or standardization. Those are 2 different methods you can use. And I did it right at the very bottom over here. So I normalized the data set by finding the mean and the standard deviation, and I took what it was, I subtracted off the mean and divided by the standard deviation. That is the normalization. So I replaced x with this. So x becomes x minus the mean of x divided by the standard deviation of x. The standard deviation is the square root of the variance. And by doing that, therefore, x will have the new x. New x will be mean 0 and standard deviation 1. And so it should vary by about plus minus 1, 70% of the time. It should be between -2 and 2 95% of the time, all that stuff. And so this makes all the x's on the same scale. Okay, and if you look at what happens in my data set that I really did this for, these were the means of all the different things. And you'll notice that the ones that have very small means, like new league, league, and division, those are the ones that were the problem, right? And the reason these had a mean, why is it that the division mean is 0.5? Well, half the players were in the division 1 and half the players were in the division 0. So when you take the mean, it's 0.5. On the other hand, things like the at-bats is in the thousands. So this was on a completely different scale than this. This was a one-hot encoding of a categorical variable, so 0 or 1. These are actually counting things. And so that was the problem before. But by doing it now, so x is now normalized, the means are this much, the standard deviations are this much, and in fact, I have an x normalized thing, and here I will delete the commented thing that says, let's set x to x normalized. Now if I was going to run this again, so x now really is normalized. If I run this again, it should say all zeros and ones. So if I do this, you see the mean of everything now is all 0, and the standard deviations are all 1. Everything is on the same scale. Everything is either somewhere between -1 and 1. And now if I rerun the whole regression, so I go back to the very top, and I run the regression again. Let's run the regression again. Okay, and you'll notice that things change a lot. Okay, wait, did this, oh, I have to make the train and test set. Okay, train and test set, and then do it. Okay, now things are very different, and now things are really comparable. Before, you could not compare one number to the other number because the x's were so different. Now all the x's are very similar. So bigger numbers really do matter more. So the number of hits you have matters a lot. The number of runs you have matters a lot. Which division or league you're in actually doesn't matter that much. It doesn't affect things too much. So it was kind of an effect before because things were not on the same scale. And now when I rerun the regression with Ridge and look at these parameters, things will look a lot nicer. Okay, wait, hold on. I probably have to do this. Okay, there we go. So now you can see all of the parameters are sort of starting out somewhere, and they're all sort of shrinking. Some of the parameters don't matter. Some of them shrink very quickly. Some of them shrink more slowly. But now it really is working correctly. And let's see how much improvement we actually got. So by doing the validation set, I can see how much improvement there was, and I can plot it like this. And now we have improved from an error of 340 down to an error of 315. So there's an improvement by like 10% now. Before it was like 0.1%, now it's like 10%. So a much better improvement. The RMSE improved from 340 to 315, and we found the best alpha value was around 100. If you go past 100, then you're doing too much, and things are getting close to 0. Okay, there's a nice real-life example, and a very common error that people make when doing this. So you have to be aware of how these things work, or you're going to make this kind of error. Any questions or comments about this model? I will tell you the other thing. All of this was done sort of by hand with I have like a little thing. I'm trying all the models, but you can also do it automatically. So there's this function called Ridge CV or something like that. Let's see if I can find it. Ridge CV. What am I trying to find? How to try different parameters. Okay. There's one how to try them parameters automatically with Ridge CV. So this stands for Ridge cross validation, and you tell it what values of alpha you want to try, and it does all the looping to find the best value of alpha with cross validation. So in this case, it found 77 was the best value that it found, and it does it all sort of automatically. So that's useful to know. And you have to be careful with these things. Again, if they don't have normalization, they won't work well. So you got to make sure that it's normalizing it somewhere in your pipeline. Okay, I think that is all I wanted to say about this real life data set of the hitters. You can also watch the videos about this data set to get more of it in the lab. They do the same one. All right, questions or comments about this one? The next thing I want to talk about, something I've sort of hinted at before, is what is the deal with multicollinearity? And so some people say Ridge will help with this, but why is this a problem at all? Multicollinearity means the data set has columns that are highly correlated. Why is this maybe a problem? Why is this a problem? I think we might have talked about this a little bit before, but let's get our brainstorming hats out. Why would it be a problem if there's a lot of correlations? And then we're going to see why does Ridge actually help. I'm going to draw some pictures for that. Let me give you a couple minutes to think. Yeah, sure. Let me give you some more time. Let me add on a minute and a half. Yeah, thank you. Let's do 1 minute. Just if you have no idea, it's okay. I just want you to sort of get your mental juices flowing a little bit before I tell you the answer, so that you at least have some frame for what's going on. But yeah, put in whatever you can think of in the next minute. I don't know is a perfectly fine answer if you really can't think of anything. All right, 10 seconds to go. Okay. And then. The. Yes, the. The. Okay. Oh, there was a word I saw that I liked. It was unstable. Where is unstable? That was nice. Unstable, it's right here. That's a nice word. Interpretability is another one. So let's see what you guys said. There's some fun ideas here. Large coefficients. So the actual size of the coefficients, again, if you rescale things, will always be around size 1. They depend on each other, making it hard to select the best columns. So yeah, this is the right kind of idea, is that when you have x1 and x2, if x1 and x2 are almost the same, and you see something, you don't know to assign the credit to that to x1 or x2. So this is like a very high level idea. This is what's going on. The relation between them is too much, but why is that a problem? That's what we're trying to get at. Higher variance is, again, not necessarily a problem with high variance, but it is this idea of you have x1 and x2 and they both contain the same information. The information is redundant, and then you're having a problem assigning the credit to one or the other. Okay, so let's see what this looks like. This is a nice one. So if you're into linear algebra, at some point you have to calculate the eigenvalues of this matrix x transpose x, where x is a big rectangular matrix with all your data. And the problem we're talking about is that x transpose x will have eigenvalues that are close to 0. So it's almost a singular matrix. So if you want to think about it from a linear algebra point of view, that's a very nice answer. Okay. If you don't like linear algebra, this is a terrible answer, though. Okay. It makes the coefficients unstable. And so what this is saying is if you ran the regression again with a slightly different data set, you would get very different answers. And this is exactly the right kind of idea. So I'm going to talk about multicollinearity. Collinearity. And the problem at a high level is, how do we assign credit? So if x1 and x2 are very related, then should we have, if we do beta hat 1 x1 plus beta hat 2 x2, should we make beta hat 1 large, or should we make beta hat 2 large? Which one should of these two, if x1 and x2 are almost the same and they're both causing y to increase, then which one of these two coefficients should we make large? We don't know which one to do, and if we rerun the model, it will sort of pick randomly. So it will flip flop around randomly. It will flip flop randomly and make it hard, making it unstable. So unstable in this situation means sometimes when you run it, depending on the exact details of the data set, it'll choose to make beta hat 1 large, and other times when you run it, it'll choose to make beta hat 2 large. So it'll flip-flop between who to assign credit to, because it doesn't really know who to assign credit to. Okay, and I have a picture version of this. We're going to go into the picture version and understand this problem in the picture version, and then we're going to see in the picture version why ridge regression helps with the problem. Okay, and basically I'm going to do a 3D version of what we saw in the very first class of the mean squared error versus mu hat graph. So if you remember in our first class, we were estimating the value of a dice roll, and we had our estimate, mu hat, and I think the true answer was 2.5. And I said that the loss function looks like this, right? The loss function was a quadratic equation, quadratic equation. So, and this height here is the irreducible error. And this is a plot of the mean squared error. So the fact we saw is the mean squared error as a function of mu hat, it was how far is mu hat from the true value, 2.5, squared plus the irreducible error. That was what we did in our first class. So there's a quadratic equation, and the quadratic equation tells you based on your estimate how much error you have. This is from the first class. Does everyone remember this picture? It was a while ago. All right. Some people are nodding, so maybe that's a good sign. We're doing a 3D version. So what do we have? We have two axes. We have x1 and we have x2. Okay. And then on the height here, okay, I lied. We don't have x1 and x2. We have beta hat 1 and beta hat 2 on the x1 and x2 axis. Let's fix that. So instead of having just one estimate, we have beta hat 1 and beta hat 2. And those are on the plane. And then vertically upwards into space, we have, the mean squared error. And there's a true fact that the mean squared error, so it's going to be some bowl-shaped thing. It's going to be like a 3D version of a quadratic equation called a quadratic form. So the mean squared error as a function of beta hat 1 and beta hat 2 is a quadratic form. A quadratic form is sometimes called a paraboloid, which is a cool name. It's a quadratic form plus some irreducible error. And again, we are trying to find the minimum value of this thing. We're trying to minimize the mean squared error. So the minimum is some bottom of the bowl. All right, that's my crappy cartoon. Here is what it looks like in Desmos 3D. In Desmos 3D, this is what it looks like. So on the x and the y axis in the plane, those are the beta hat 1 and the beta hat 2 values. And this green cone on the height, the z, is how much error you have as a function of beta hat 1 and beta hat 2. And the beautiful thing about Desmos is that you can give it a little spin. Let's give it a little spin. Ooh, look at that. Amazing. Okay, don't go too fast. There we go. Beautiful, nice, slow spin. So this bowl, and it has a minimum here. That is the true minimum. That is the true value of beta hat 1 and beta hat 2 that we're trying to find. All right. Everyone with me so far with what's going on in the graph? It's good? So you might notice this bowl is perfectly circular. This is a circular bowl. And a circular bowl is what happens when there is no correlation at all between x1 and x2. So right now, the coordinate for the x's and the coordinate for the y's, for the beta hat 1 and the beta hat 2, they are uncorrelated, and you get a circular bowl. Now I'm going to change the correlation, and we're going to see what happens to this bowl. So this bowl, it's always a so-called quadratic form, a paraboloid, but its shape can be slightly different. So I'm going to change this slider called C. C is for correlation, and we'll make it a little bit bigger, and you guys tell me what happens to the bowl. So the bowl, oh no. Oh, there we go. So the bowl is getting longer and longer and longer and longer. And here's a C is 0.995 to really exaggerate that effect. So this really still is a paraboloid. It's a bowl, but what do you notice about this bowl? Who can tell me, if I came to your house and I said, let's have some soup in this bowl, what's wrong with this bowl? What's the problem? Why is this a bad bowl for soup? Yeah, say that again. Oh, it's open on one side. Yeah, so if you zoom out, eventually, okay, wait, hold on. Let me see if I can zoom out. So, it goes on forever, and eventually it's like bowl-shaped. But, so the computer cuts it off right at the end of our view. If you zoom out, you really do get a bowl, but I would argue it's a bad bowl. It's not a good bowl. Tell me what's wrong with my bowl so I can go home and buy a better bowl. Yeah. It's too narrow. Yeah. It's too narrow. This is way too narrow. There's one direction on which it is extremely, extremely narrow, and on the other direction is very steep, right? So before it was perfectly symmetric. But now it has this really long direction where it is very steep. And what this is saying is that there are a lot of different values. Let's zoom back in. There are a lot of different values of beta hat and beta 1 that have almost the same error, right? So this green dot is the true minimum. But if I go a little bit to the left on the long direction, I have almost the same error, right? The height of the function is almost the same here as in here. They're almost the same. It's hard to tell those 2 points apart. In fact, you can have a whole line. You can determine the direction of this line. The direction of this line is x plus y going through a straight line going through there. And that's the direction in which there's a lot of ambiguity, right? I cannot tell apart beta hat 1. I think the true values are, what are they, 1 and 4? 1 and 4. 1 and 4 is the true value here. It's hard for me to tell apart 1 and 4 and 2 and 3 because the height of the function is almost the same, right? And that is saying exactly, this is the math version with a nice function of exactly what we said before, that it is hard to tell apart beta hat 1 and beta hat 2. So this goes to the mean squared error loss surface. This surface that we're talking about, sometimes called the loss surface, is flat along beta hat 1 plus beta hat 2 equals a constant, right? So it has this long direction where I cannot tell apart the beta hat 1 and the beta hat 2 because the surface is very flat. Okay, and you can really see this manifest. So this is the true value. Of course, in real life, you never get the true value. You get data, and that is what I have over here. So I have some data. So here are some x and y values that I got. Let me put on the x and y values. I want the loss surface of the x and the y values. Here's the estimate they came up with, I think. Okay, and then here is, no, that's the function g. Hold on one second. Here's the f. Okay, yeah. So in blue, the green is the true value, and the blue is what you get from some data. So the blue is not exactly the same as the green because you have some random data, so it's got shifted a little bit left, a little bit right, just by random chance. You rolled the dice 10 times, and you don't get exactly the green, you get the blue. And the blue loss surface is very similar to the green surface, except for its minimum is all the way over there. So the minimum value of that blue surface is that blue dot, and you can see that it is quite far away from the true value. However, it's still close to that line. So, and as I change the random seed here, you've seen this a number of times, how I change the random seed. So here, as I get more and more data sets, you'll see that it's unstable in the sense that the beta values are far away from the green values, right? The estimates you get are far away from the true estimate, but they're always close to that line. So in other words, the individual value of beta hat 1 and beta hat 2 are changing, but the sum of them is pretty stable. So they're individually unstable, even though the sum of them is stable. This is the math version of the problem we said before. Okay. Questions or comments about that? Anything make sense? We're about to add in the ridge. We're going to add in the ridge right now. Okay, let's add in the ridge. Let me pause this thing before we have a problem. Let me actually turn off the data, the blue function f. Okay, turn off the blue, and we'll turn off this. Okay, let's add in the ridge. So to add in the ridge, we're adding in this function, which looks like this. It's right now it's in gray. And it's the function alpha times x squared plus y squared. That is the penalty that we had before. And I'm going to add it on like this. Let me turn off this green one as well for now. So I can change the value of alpha. This is a bowl that is centered at 0. Why is this a bowl centered at 0? Well, remember, the x and the y-axis here are beta hat 1 and beta hat 2. When we do the ridge regression, we add on this bowl. So ridge regression, we're literally adding on the function alpha times beta hat 1 squared plus beta hat 2 squared. That's the function that I've plotted in gray over here. So we've added on this gray function. And depending on the strength of the alpha value, we can add a very steep function or we can add a very small function. And we literally take this gray bowl and we add it to the green bowl. So the green bowl was over here. That was what we had before. What happens if I take this green bowl, which is has a really long direction. Let's zoom out again. So we can see the long direction. And I add on a big gray bowl. So the actual thing, when I add in the ridge regression, I am adding on this circle. And you can see as I make it stronger and stronger, the really long green bowl becomes more round. So you can think of what's going on when we add on this thing. Let me animate this. The stronger the alpha value is, the more steep of the gray bowl, and you add that on to the very long bowl from the problem, and it becomes more round. So the effect of this is sort of mathematically, this whole thing has a rounder bowl than just the mean squared error alone. A rounder bowl than the mean squared error alone. So the mean squared error has this very long direction when there's collinearity, but by adding on this regularization term, which is perfectly round, it is helping to fix that. You can also express this in terms of singular values and eigenvalues. So x transpose x plus alpha times the identity is more invertible, less singular than x transpose x. So if you like linear algebra, that is how you would phrase the same fact. I'm not going to get into linear algebra. I'm just going to say it has a rounder bowl. Okay, and what is the effect when you have a rounder bowl? Let's put the data back in. So let's fix some alpha value. What if we fix an alpha value of, let's say, 2 or 1.5? That's a good amount. So at 1.5, right? Remember, it started out like this, extremely wide. At 1.5, we have done a pretty good job of shrinking things down, making it pretty good. And now, if I take a new data set, let me turn off this. Now, if I take a new data set in the blue, like we put the data set back in, where's my data set? F. Here's the blue bowl from the data. And the thing is, because it's rounder, it doesn't move around as much to the left and the right. So now if I put in the value of P and Q over here, where's P and Q? P and Q. Okay, it's over there. Here, we can look at it from the bottom. Okay, there we go. We'll look at it from the bottom. And now if I re-roll the randomness, you'll see that it's a lot more stable. So for the ridge regression, remember before I put in the alpha value, it was jumping around all over the place, but now it is quite stable, and then the reason it's quite stable is because the bowl is a lot rounder. The bottom of the bowl is jumping around less when you move it over a little bit. So the ridge regression value is much more stable than it was before. You'll notice it's quite close to 0 over here, so maybe I over-regularized it. I put in too much alpha. Maybe I should slide the value of alpha down a little bit. But where's the value of alpha? It's over here. So 1.5 is maybe too much. Let's go down to 0.7. That's a nice number. And so now it's jumping around more, but this has already had stabilized it quite a lot. So maybe I can go even less. If I go like to 0.2, just a 0.2. Look at before it was jumping all over, up and down and up and down. Now it's quite stable over here. So it's finding a solution where the sum of the squares is that penalty term is making the bowl rounder and taking this long direction that is very unstable and kind of stabilizing it. Here's what it looks like from the side. We'll go a nice smooth thing like that. Okay, that's why ridge regression, it helps stabilize things. It makes the loss surface, this thing you're minimizing, it makes it a lot easier to deal with because it doesn't have this long direction that is very unstable. That's my picture explanation of multicollinearity. I guess I can also post, I have some recordings where I do the linear algebra explanation, but I think it's a little more technical and not as intuitive. Any questions or comments about this one? Okay, so that's why ridge regression helps with multicollinearity. It helps stabilize things. So like I said, on Monday's class, there'll be a guest lecturer, not me, and they will talk a little bit about the lasso. And the lasso also does this kind of thing. So the lasso is here. That's a purple surface and a purple dot. But the lasso, interestingly, has some other properties. So you'll see that. Let's look from the bottom again. So the ridge, right? Okay. Let me zoom out and try to get this in the right spot. This is all flip-flopped from my brain. Okay. Can we sneak in on it like this? Okay. Can I rotate this way? Okay. So, all right. Here's the plane. So we're looking at it from the bottom. The green is the true center. The ridge regression we did stabilized it. It made the bowl rounder, and we're finding this nice solution over here, which is somewhere in the middle. The ridge solution is always hanging out over here. The lasso solution, that's what you guys are going to do on Monday, is also stabilized in a certain sense. And you'll notice it has a very funny property. Sometimes it's up here near the true answer, and sometimes it's down here near this answer. So it's going sometimes over here, sometimes over there. But it has a really nice property. Does anyone notice something about that purple dot that is quite a nice property? The purple dot. Where is the purple dot, typically? Yeah. Exactly. The purple dot is exactly on the axis. And when it's exactly on the axis, that means either beta hat 1 or beta hat 2 is exactly 0. So the ridge regression stabilized things, but both coefficients are still there. They're both, instead of being 3 and 1, they were 2 and 2. But the lasso, it has the property that it is setting some of the coefficients to 0. Sometimes it sets beta hat 1 to 0, and it's getting a solution near 4, 0. Sometimes it sets beta hat 2 to 0, and it's getting a solution near 0, 4. Why is it doing that? That's what you'll have to see on Monday. It's very useful to eliminate variables because then you don't need to measure them. You can imagine in real life you pay money to measure the variables. So if you can eliminate some variables, set them to 0, that will save you big bucks in real life. Okay, that's what you're going to do on Monday. I don't know if they'll actually use this demo. If they don't, I will do the demo for you maybe next Wednesday. But they will tell you something nice about the lasso. Okay, any last minute questions or comments before we adjourn for the weekend? All right, have a great weekend, and I'll see everybody. Please come to class on Monday for the guest lecture, but I will personally see you next week, next Wednesday, when I'm back.